Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! Okay, so today's show is on quantum mechanics theory, which is kind of hard to talk about, mostly because it's like, you know when you watch a superhero TV show that you really like, and the characters are always doing something unbelievable or impossible, and it's important on these shows that there are rules. There are rules to what Supergirl can do and what she knows, and it's important that we as the audience understand them as well as Supergirl understands them, so that the audience can feel dramatic tension and anticipate what comes next. So like, you watch the show and understand the rules and love the plot. But then you try to describe the plot to your friends who don't watch the show, and it's kind of boring and weird for them because they don't know the characters and they don't understand what the rules or limits to what Supergirl can do, so they can't imagine what you are talking about or why it's interesting. That's what it's like to be a physicist explaining quantum mechanics. And that's also what it's like being a non-physicist trying to follow one of these explanations. There's just too much stuff that you haven't heard of. So it is any wonder that people can get the wrong ideas when you try to talk about how a quantum system can be two things at the same time, or how a quantum cat can walk through two different doors at the same time. And then they go and try to buy a special metal bracelet that uses the magic of quantum. It's bonkers. It's like the person you were trying to explain the Supergirl TV show to heard the part about flying around and picking up cars and didn't really understand that these things only happen in a specific context, so they went out and jumped off the roof of the garage? Today's episode is about how quantum mechanics fits in with the rest of the world which does not seem to act according to the rules of quantum mechanics at all. It's a concept that lets us talk about why some systems act all weird and quantum-y and others do not. To extend the metaphor, we're going to talk about how Kara Danvers and Clark Kent put on glasses when they're going to stop acting all super. Today on the Titanium Physicist podcast, we're going to talk about quantum decoherence. Now, you've already heard the voice of our guest today. He's an amazing musician and songwriter, headlining his own eponymous band, and also being half of the musical duo known as The Both. But he's also a podcaster now. His show, The Art of the Process, co-hosted with Amy Mann, explores the creative process by interviewing other notable creative people. He was also voice cast in the Steven Universe movie. Welcome back to the show, Ted Leo.
Thank you. That's the best introduction I've ever had.
All right, Ted. I've got two amazing titanium physicists, and they are going to carry us through all the way to the end today. Arise, Dr. Danica Marsden.
Whoop, whoop.
Dr. Marsden is a physicist who did her undergraduate with me at UBC and then a PhD from the University of Pennsylvania. Afterwards, she was a postdoc at UC Santa Barbara, where she did research on MKID detectors, and she also worked as a project manager for D-Wave Systems, the quantum computer company. And now arise, Dr. Stephanie Simmons.
Bing!
Dr. Simmons got her bachelor degree from the University of Waterloo and her PhD from Oxford University, and she's currently an assistant professor in physics at Simon Fraser University, where she's an expert on quantum technology development. All right, everybody, let's talk about coherence and decoherence. Okay, Ted, one of the questions that we'll be answering today is, you've heard about Schrodinger's cat, which is alive and dead at the same time, paradoxically. Why don't we see that in the large scale world? Why does that seem to only fit in the domain of particles and stuff? And the answer to this kind of paradox involves a new concept, which we're going to call coherence and decoherence, and a process. And so it's going to be fun. So let's start actually with kind of a model that we can use to put some of these rules and concepts into context. Have you ever heard of the double slit experiment?
I have, because I was looking to try and figure out how some of these ideas I knew we were going to be talking about map with what I know about wave coherence from audio engineering and stuff.
Okay. So usually physics students hear about it at the start of their second year, and it's kind of a mind-blowing idea. And the process involves kind of three parallel experiments. In all these experiments, what happens is you get a box, and by a box I mean it's about the length of a table. Maybe it's not necessarily a small box, although it can be. And in this box, you've got three boxes: one that's kind of half full of water, and one with a light bulb in it, and one with an electron emitter in it. You start with the water one, and halfway down the box, you put in a piece of a board with two long slits cut into it vertically. Okay. And then so you put it about halfway down.
I'm doing this. I'm following along and doing this as we go.
Oh, good. And then you go to the far left-hand side of the box, and you make some waves on that side of the box. And the wave front will move out, expand, and then it'll hit the board and the two slits, and only part of the wave will be able to travel through the slits. And then so you'll get one little circular packet of waves going through the left-hand slit and one little circular pack of waves going through the right-hand slit. And those will move on and hit the back wall. Yeah. Mm-hmm. So those two waves, when they hit the back wall, those two wavefronts are going to interfere. And so instead of one up and down kind of sinusoid on the back wall, the two waves as they interfere, they're going to be really high in some places and really low in other places. And that's the basic principle. You get this interference of these two wave packets. Does that kind of make sense?
The wall creates the interference.
Sorry, there's two wave packets, and they're both kind of waving up and down.
They're not in sync after they come through the slits, is what you're saying?
Well, okay. So the idea here is that as those two wave packets expand, they're going to kind of hit the wall at different times, and so they're not going to be completely in sync where they hit the wall, depending on where on the wall you look. And so there's going to be some places where those two wave packets interfere constructively, and some places where they're going to interfere destructively, and it's going to be a really wavy time. Yeah.
Mm-hmm. Like, it's similar to when you're standing in a pool, and this is actually Steph's analogy, but you put each of your hands in the pool and create a wave. And then as those waves kind of propagate out and they come into contact with each other in different places, they're going to add up or cancel.
Right.
It's the exact same thing as sound, right? Superposition is totally normal, everyday thing. It just also works when you apply it to individual particles, which is where things get weird.
So stop me if this is going too far afield at at this early stage, but is that, because of the medium? Because like in a vacuum, those waves, where they're not water throughout the base of the box, for example, whatever came through the slits would not interfere, right? Not until they hit the wall.
Oh no, they totally would. They totally would the whole way. So for example, in space, there's no medium, or at least not one that meaningfully makes any sense. But yet the photons that are traveling through that show all this interference.
Okay. Interesting. All right.
I mean, so the principle with doing it in a big water box isn't that it's particularly illuminating. It's just an easy way to visualize these two waves. One of the wave packets, they both started as the same wave because you splashed your hand up and down on the far left side of the box. But then as that wave hit the two slits, that generated two kind of sibling sets of waves that went on to interfere. And you're like, okay, well, I'm not going to do any complicated physics, but I know the idea that these two wave packets are going to hit the wall in different places and kind of make a weird interference pattern. And so it's up and down and all choppy. Fine. So then we reproduce the experiment with light. So in classical physics, light is an electromagnetic wave, which means that it has a wavelength and frequency. And so you take your light bulb and then you shine it, and it goes through the two slits. The light wave passes through the two slits. And then on the back wall, essentially the same thing happens. Instead of one light wave traveling outwards, as it goes through the two slits, you end up with two sibling sets of waves, each one coming through the two holes. And then those two wave packets are going to interfere on the back wall. Does that make sense?
On the back wall.
No, they interfere the whole way along. It's just at the back wall is where you see the result.
Yes.
Yeah. So it's like you've got two trumpeters in a room playing. You're going to have different points in the room where, as soon as the sound emits from the trumpet, the whole time, those two different sound waves are interfering and constructively and destructively with each other. And we're just bringing that up first, the water and the waves, because that's something that we sort of understand, but it starts to get a bit strange when particles act that way. And that's why we're kind of starting with the water waves experiment.
But the math is exactly the same, right? So the analogy is very precise.
Mm-hmm. And also, I want to point out that Steph keeps bringing up something about how the waves are interfering everywhere, and it's true. And if you looked at the water box, you could see them interfering everywhere. But the thing about light is you can only tell where these light waves are by, sticking something in the way. And so we can only see them interfere on the back wall. But that interference between the two packets is going to interfere in a really specific way. It's going to make they're called fringes. So we're going to see bands of bright light where the two waves are interfering constructively, and bands of dark where they're interfering destructively. Does that make sense?
Yes.
Yeah, so I guess that's why you were mentioning the back of the wall is just that acts like our detector for seeing what the pattern looks like at that point.
Yeah.
Can I throw a layman's visual eye question at you regarding the light wave interference? So, that said, you're gonna notice it the most when it hits the back wall, but visually, light, is diffuse as it projects. It's not like there must be multiple. It's not one single wave. There's a wave packet or something, right? That like diffuses throughout the space as it goes along. So they're going to be interfering along the way. Is that correct?
So if we could pause time and see what the light was doing, the way we would take a photograph of the water in the box, you would see one wavy up and down circular wave being emitted from the one of the slits, and a similar up and down circular wave being emitted by the other slit. And then every place on the right hand side of the box in where the two parts are interfering, you would see those two bands of waves going up and down interfering. So they're interfering at every location.
Right.
The deal with the back wall is it's kind of a measurement device, if you think about it. And I've been glossing over the idea of measuring, but over the course of this conversation, the idea that we're measuring the system is going to become more and more important.
Okay.
So, one of the aspects to this, though, is if we changed where the wall was located, if we moved the wall forward or backwards, the location of those interference bands would change. The locations on the wall where the bright lines are and the locations on the wall where the dark lines are would change. If you brought them forward, they'd move left. If you pushed the wall back, they would move right. So in a way, when we're putting the wall there, we're getting a measurement of how those two waves are interfering along that line. Does that kind of make a sense?
Yeah. Mm-hmm.
But one other aspect I want to emphasize here is the idea that the intensity of the light on the wall is kind of a description of this interference. Where it's really bright, those two waves are interfering constructively. Where the two waves are interfering destructively, then it's like a dark place. And then you go, okay, well, that's very interesting. And then you move to your third double slit experiment, which is something very similar. It's an electron emitter. Now, one of the first things people figured out in quantum mechanics is that particles have wave-like behavior. Have you ever heard that?
Yes.
Yeah. And so the double slit experiment, because particles have wave-like behavior, the double slit experiment should work on something like an electron. So what you do is you set up the box just the same, only instead of a light bulb, it's an electron emitter. And the thing about when you're talking about waves for quantum mechanics, you're kind of talking about waves of probability. And so they're traveling outwards, and essentially you imagine the same thing as you do with light, as you do with the other box. There are wavy waves, they go up and down. Their up and downness is kind of a measure of the likelihood of finding the electron in that location. But so you have a wave and it goes out of the electron emitter, and this wave that represents the electron passes through both slits at the same time because it's a wave. That's what waves do. And then from each of the two slits, you get little circular waves emitting, and they hit together on the back wall and they interfere, or they should interfere the way that the light waves did and the way that the water waves did. Does that make sense? At least logically, that's how waves work.
Sort of, except that if you're sending a single wave, are we talking about like sending a single electron?
Yes.
Okay.
Yeah.
Yeah.
And as much as Ben's describing what we know now, that is one of the weirdest things when you're thinking about a particle going through a gap. You wouldn't expect it to necessarily, intuitively have, from our experience, have an expectation that it would act like a wave.
So, like, in other words, if the slits in the board are at a position to essentially bisect the electron wave coming at it, then what happens on the other side of those slits is the real question of like what we're going to be talking about.
Yeah. Well, that's where we start. And so in this experiment from second year university, the wave front representing where the location of the electron is somehow passes through these two slits. And then on the other side of the slits, you get a weird interference pattern. And on the back wall, you will get an interference pattern just like you did in the light box. But notably, the electron isn't everywhere, kind of. I mean, when an electron hits something, that's a particle hitting something, right?
Mm-hmm.
So notably, what happens is when it hits the wall, you'll just get one electron hitting that wall. And maybe you've set it up so that you can see where it hits. And you'll be like, oh, well, the electron hit at that location. The wave represents where the particle could be. It's a probability idea. And so to see the results of this interference, you have to run the experiment over and over and over with lots of different electrons, one after another. But if you do that and make a mark every location the electron hits the wall, you'll see interference fringes the same way as you did with light. There'll be some places where all the electrons are hitting along these bands. And there'll be some locations of the wall where those two waves are interfering destructively, where you won't see any electrons hitting.
It should be said that happens for photons too, right? Like you get that pixelation happening.
Yeah.
Yeah.
So it knows generally where it's allowed to land on the other side and where it's not allowed to land on the other side.
Okay, hang on a second. So, all right. So when we do this slit experiment with an electron, are we saying that we're still only getting a single wave, and then probability, will tell us like where the multiplicity of other waves might hit? Or are we saying we actually get two waves on the other side of the board with the slits?
The interference pattern is coming from these probability waves interfering with each other and constructively or destructively interfering, creating the pattern, and then that somehow dictates then where the electron's going to wind up. And it somehow knows.
But it's one wave for that one particle. Okay. It just has all this structure to it, right? So you're just basically asking, like, how many terms are you writing out in your mathematical equation, as it were? Is it one? Is it one term? Are you talking two terms? Like, is that two waves, or is that one wave that is two parts? I mean, that kind of, in a way, it doesn't matter. The math doesn't change. And also, what are you measuring against the wall? Are you measuring one term with each, blast of the particle, or? Well, at that point, you're measuring one, like, click.
Okay.
Yeah. So what's interesting is measurement really dictates what you will see. Like if you're measuring at the back wall versus right at the slit to see where the electron goes through, that will change the whole experiment results.
Yeah. Okay. So you take your second year university student and you tell them about this. And just like you, they're like, hold on, that doesn't make any sense. And you're like, no, it does. You see these interference fringes. The presence of the interference fringes, when you run the experiment a whole bunch of times and you look where all the electrons land, the presence of the interference fringes means that the electron definitely is a wave, the same way light is a wave, the same way water waves are waves. Because particles wouldn't do that. If it was just a probability distribution and we just didn't know where the particle was, you wouldn't get interference fringes. You would get overlapping probability clouds. So you would be like, okay, well, if it went through the left door, you'd get a cloud of likelihoods around the left door. If it went through the right door, you would get a cloud of probability distributions around the right door. So you'd look on the wall and there'd be kind of two bright spots on the wall. You wouldn't see this weird interference. And so you say, listen, you run this experiment and you definitely see the interference fringes. That means electrons are waves. And then the university students go, oh, no. Okay. But at this point in the game, you start introducing the concepts that we've built for quantum mechanics to explain what's happening and also explain some of the mysteries. And the issues that you're already cluing into are some of the reasons that we need to introduce some of these concepts. Okay. So, for instance, one of the concepts is called wave-particle duality. It says a thing is either a particle or a wave, and it's either one or the other. If you expect it to act like a particle, it'll be a particle. If you expect it to act like a wave, it'll be a wave. So if we ask ourselves, okay, which door did the electron actually go through? Say, okay, this probability distribution, this thing that's interfering, this wave that's interfering with itself, that's just an abstraction. In reality, I imagine that there is an electron. It must have gone through one of these two holes. Which hole did it go through? If you ask yourself that question, you don't get a good answer. So imagine you put a little detector to see to measure which of the two doors the electron went through as it goes on to hit the back wall. As soon as you do that and ask, okay, is this thing a particle? The wave interference fringes on the back wall disappear.
Oh, I really don't like that characterization. I'm sorry. Can I voice a complaint there?
Yes.
Okay, so imagine here's a picture, right? Here's something that's both a particle and a wave at the same time. It starts as a flat line, and then it squiggles kind of like a sinusoid up and 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 then back down to zero, right? That thing is an object, and send it through whatever that is, whatever is oscillating up and down, that's a thing, right? That has a spatial contribution, right? Because you can send that off that's wave packet is the word that we use, but whatever. It has a wave character, but it also has a position associated with it, right? You can say, okay, the middle is around here, and if you move it around, it'll still have a middle, right? So that's the way to think about it, because you can measure its wave-like properties, because that thing still has wave-like character, or you can measure its position properties, and they'll have a position affiliated with it, right? It's not the end picture, but that's the way that I would start the discussion, because that's how you can see how these things can be at the same time. It's not as if the particle goes, oh no, hang on. Ben really, really wanted me to be a particle. I better pretend, right? Because that's not the picture, right? It's what you measure, it reveals different measurements, but you can have a structure that supports both a wave-like property and a particle-like set of properties, right? That's not impossible.
And that's not the same thing as just a particle behaving in a wave-like manner?
The point is that everything has these characteristics. Everything has a wave-like character, and everything has a particle-like character to some extent, right? It's just
okay. I get that. Yeah.
It's not as if it's toggling between the two. It's that it always has both, and when you choose to measure a certain property, it will reveal that kind of result. Right? That's the thing.
But it will also constrain how, so an electron can be existing, we'll say, in a cloud of locations that's sort of represented by a probability distribution. But once you are making a measurement as to its location, that kind of information forces a particular location to be revealed.
For sure. Yeah. So measurement is a whole other part of this. I didn't want to get into just yet, but yeah, measurement then changes what is left over as it were, like what happens next. Like it says, oh, I have to be in this position. And so everything from that onwards has to be consistent with that result. But that doesn't change the fact that as it's, evolving in time and moving or doing whatever, it still will have particle and wave properties always, right?
Damn straight. So essentially, the deal is that these particles aren't particles, and these waves aren't waves. They're both at the same time. You introduce the idea that it's kind of both at the same time by introducing these contradictions to people, but you can't stop there, like Steph says. And so how do we describe, in terms of the concepts that physicists use to break down quantum mechanics, how do we describe this system? We do it in terms of something called states. So the deal is, at the start, your electron is in one state. It got emitted from the thing, something happened. And then, as it goes through the two slits, suddenly there are kind of two places this wavy, particly electron thing could be. The left-hand entrance and the right-hand entrance. And then so past there, because you don't know which one the particle wavy thing went through, and it kind of went through both, past there, the system, the electron, is in two states at once, at the same time. It went through, this particle wavy thing went through the left-hand door, and the particle wavy thing went through the right-hand door at the same time. And those two states end up, as they exist together at the same time, end up kind of dictating where the particle could be in the future.
And a state is sort of a collection of information. So the left-hand state is the collection of information that says the electron went through the left. And then likewise, the other state is where the electron was in the right side. And in this case, there aren't really other properties that could contribute to more states for the purpose of this experiment.
Right. There's no other interference, external interference within the box on the other side of the board.
Well, you could have, electrons can have spin up or spin down as well, but we're going to ignore that for now.
Okay. Thank you.
Yeah, there are other degrees of information in the system than just which door the electron went through. But the idea is that exactly how the system evolves after those two go through the door is consistent with the electron having gone through both at the same time. It's a superposition of the two states, just like how in the water box you would say, well, the height of the water at any location is a superposition of the two wavefronts. The wavefront from the left and the wavefront from the right. It's like the wavefront from the left is one state and the wavefront from the right is the other state. And then everything forward is a superposition of those two states.
Right. Okay.
Then we come to an interesting concept, which is measurement. When you do a measurement, you're essentially asking the system which state it's actually in. Did you go through the left door or did you go through the right door? Your measurement ends up forcing the system to decide which of the two states it's in. And in other circumstances, we describe that as the collapse of the wave function. Essentially, the information that you know about the system, which is that it could have gone through the left-hand door or could have gone through the right-hand door. As soon as you ask the system a question by doing an experiment, essentially putting a wall in the way so that it can't be in both places at once, that forces the system into one or the other. And the thing about quantum mechanics is that which system it ends up in is entirely probabilistic. It's a roll of the dice. It's like, okay, well, at that point, you say, okay, system, which state are you in? And then the electron rolls some dice and goes, oh, well, I rolled a 2, so that means I'm over here. Or I rolled a 1, so that means I'm over here.
So you don't need like a PhD to do the measurement either, right? Like when photons are emanating or bouncing off a thing, they travel outwards as waves and go out in all directions. But when the photon hits your eye, it, like, right before it hits your eye, it's this big wave that's all over the place. And then it collapses, the photon that does manage to get in your eye, that says the photon has collapsed, as it were, to that position. So it's not like it's something you need to have a lab coat to do. This is, measurement is something where the environment is extracting information, and that environment can be an observer or it can be whatever.
Right. And because two people can see photons from the same source of light, you start to get more information as to the vast probability that could exist.
Sure. Right. And so like when you're putting the detector wall at the back end and you're running photons, like you're running hundreds of billions of photons, those are each individually traveling as a probability wave, and then it has answers with some probability, and that builds up that pattern at the back wall.
Yeah, I think I understand that.
Okay. So to review, the story I'm about to tell is the way that people who know how to do quantum mechanics would describe the system. Instead of talking about waves and particles, we say, okay, so your system starts out on one side, and then the system goes through the two slits. And then afterwards, the system is in a superposition of two states, the state where it went through the left slit and the state that went through the right slit. And from there on, so for everywhere on the right-hand side of the box, which part of the wall the electron hits, from there on the right-hand side of the box, it's a superposition of those two states. You can only predict where the electron's going to end up if you consider that it is both states. Yeah? And so you have to say, okay, it's a superposition of both states, and it will be a superposition of both states until you do a measurement. And the measurement is putting a wall somewhere for the electron to bounce off and light up and be detected. If there's no detection in there, then the system will be a superposition until you do a detection. So if you move the back wall farther away, the system will be a superposition until the system interacts with that back wall and you do a measurement. So it's kind of a story about information. First, we have the system is in two states at once, and then the detector extracts the information about where the particle is, collapsing the wave function, stealing the information out of the system. Does that kind of...
One other thing is that the question you're asking with a wall at the far end is, where are you along that wall? You're not measuring which aperture or which slit it went through, right? There are different ways, different measurements you'd set up to ask that question, right? You'd put filters or something in front of each of the different slits to like mark the photon or the electron or whatever. But what you're setting up with the back wall is a measurement of the probability wave back there. And given that it's been interfering that whole way, you're not actually asking the question, which door did it go through? You're asking, what position is it in now?
Where is the electron along that wall? Where does the electron fall?
But can you deduce backwards from that point, to figure out which slit it came through? Because, the probability is not going to be infinite for each slit, right?
Well, no, that's the point. Like, you can't back it out because, well, you can in the sense that it had to go through both, which is that's the crazy part. One electron had to go through both slits to get that interference pattern. And when you change the measurement to be where is the electron at that point in space, like at the location of the wall with the two slits, by changing them, what you're asking in terms of the measurement, you're changing the result, which is that then it says the electron went through the right slit, but then you don't get the interference pattern on the further down wall because now the universe has to remain consistent. And once it knows it went through the right slit, it can't interfere with itself anymore, and it can no longer make that interference pattern.
And the analogy with the water is precise here, right? Like, so if you're thinking about the oscillation of the waves at the back wall when you're making those two splashes with your hands, I mean, when you're asking, okay, so fine, you get some amplitude at the far end, which hand did that wave come from? Well, it came from both, right?
Mm-hmm.
Right. Okay.
So, and actually Ben had a good, has a good analogy around a baseball, which is this idea that if nobody observes a baseball, kind of like Schrodinger's cat, it could be anywhere between, the pitcher's mound and the back plate in quite a huge variety of places. But as soon as there's light bouncing off of it or people watching it, that's a sort of constant observation where at each moment in time, the universe has to remain consistent and we all see it in one place and then the next place and then the next place. And so the superposition of all of the particles that make up the baseball are,
being measured.
Yeah, it's being constantly measured, and it limits which of the possible states the ball can be in a superposition of.
So another way to say this is imagine we were doing the double slit experiment with the particle again. And instead of asking the question, where on the back wall is it going to hit, we did an experiment to ask, which of the holes did it go through? Let's say we set up a little screen over top of one of the slits so that if it was going through the left hole, it would hit the screen in front of the left hole. And if it was going through the right hole, it would just pass through the right hole and then hit the back wall. If you did that, you would extract the information about it going through the left hole or versus the right hole. And because of that, it wouldn't be in a superposition past the double slit area. And so it wouldn't be a superposition anymore. And so these two superpositions wouldn't interfere. The idea here is that doing a measurement is actually going to change the nature of kind of how we describe what's happening. And if you do one measurement that says, hey, which of these two superpositions are you in? It's going to stop being in a superposition and it's going to stop behaving like it's in a superposition. So the measurement that we do changes the system.
Okay, yeah, this gets really philosophical because to my brain, I want to ask, like, does it or does it not just measure the way that this particle went through the system?
The simplest way to explain this is like, imagine that you're playing pool in the dark and you want to know where the 8-ball is. The only way to do it is to, launch the cue ball in certain directions and listen for a clicking sound, right? But as soon as you've done it, hey, the 8-ball has scattered off somewhere, right? So you know where the cue ball was, but in interacting with it, you've modified the system.
Right.
Oh, I have such a great analogy. Do you guys remember in Mario Brothers when you'd be like going along and there's a ghost behind you? And when you're going along and the ghost is behind you, it's kind of moving around and you don't know where it is. But the minute you turn around and look at it, it stops, it freezes it.
Yeah, it hides its eyes. Yeah.
Right. So observation, measurement, it sets up the parameters for what you know about the ghost. It nails it down.
Yeah, you can't do a measurement without affecting the system. If I want to know a piece of information about the system, extracting that piece of information from the system is going to change the system. It's like the idea that, the information about the system is a conserved quantity.
So the summary is that superpositions
don't
survive measurement.
Got it. Okay, that makes sense. I get that.
Right? So superpositions are wild and wonderful and continue on, but as soon as you measure information about it, then they have to collapse down.
Right.
Yeah.
And it may set up a new system of superpositions, but just not the ones that were there previous to the measurement.
Yeah. But it has to be consistent with the measurement that you took.
Right. Okay. Got it.
Right. So it has to snap to some value.
Yeah.
And now it's time to talk about systems that aren't ideal. So here's the thing about light. In our experiment, you go, okay, so I've explained this all to you, and then we go back to our table and we start wiggling with the right-hand wall of our wave boxes, our double slit wave boxes. No matter how far you put the wall back in the light box, you're still going to see these interference fringes. When you do the experiment with the electron, the farther back you put the walls, the interference fringes kind of blur out. They go away.
There's caveats with all that stuff, right? But basically, photons hold on to that interference pattern for quite a while, and compared to matter,
the age of the universe.
Yeah, so light travels through almost everything, or it travels through air, it travels through gas, it travels through vacuum, all pretty much the same. It needs to hit something a little bit solider to kind of damp away. But the particle in the box, we're doing it on a tabletop. It's not in a vacuum. So there's air, and the farther back I put the back wall, the more air the electron has to go through in its interference fringes, doing that thing before it hits the back wall. That air is kind of mucking up the experiment.
Yeah.
And it's interacting with, perhaps. And in a way that means that the air creates this environment. So if the electron is your system, then the environment is made up of this air that's interacting with it and in a way kind of measuring it.
Yeah.
Information is sort of leaking out through these interactions, right?
As it goes through any medium, that would happen, right?
And you don't even need necessarily a medium for stuff that has mass, because there is information leaking out because it has a gravitational effect on something, right? Like everything is connected to everything else through gravity. And so in some very weak way, anything that has mass has information leaking out about its position all the time because of its gravitational effects on everything else.
Wow.
So we end up with a new framework for talking about these things. Because until now we've been talking about this idealized system where you kind of imagine that it's in a vacuum, you have to start saying, okay, well, if your system is your electron interfering with itself inside the box, if I do my measurement, I can extract that information from it. That will change the system, but that's fine. I have my measurement. Good. And then you add a third player. The third player we'll call the environment. And the idea is, if the environment can interact with the system, the environment's going to start picking information out of the system at random. It's going to do its own little baby measurements, right? The electron, as it moves through, maybe the electron is an air particle. It's going to be like, hey, instead of interfering with your brother, why don't you interact with me? And maybe part of the electron's like, yeah, okay, maybe. And that messes up the experiment past that. So the idea here is that the environment is kind of stealing information away from it, and we lose this nice experiment that we've been talking about, this idea that there's a third player called the environment. And so here's where we introduce the words coherence and decoherence. Ta-da! We say that the system, when it's in a superposition and it's pure, it's a coherent system. And when the environment extracts information to the point where you can't do the experiment anymore, that's decoherence. So the environment interacting with the system is the process by which decoherence happens. And it's this marvelous idea, which in part explains why the large-scale world doesn't seem to operate by quantum mechanical rules.
Does decoherence in this sense have any similarities to what I would be familiar with as like phase shifting and phase cancellation, as sound waves move through air and arrive at receivers, ears at different.
Yeah, there's different kinds of decay. There's different ways that coherent states or superposition states can decay, and that's one of them. Right? And the wave analogy there is actually pretty good. There are other. It can get much more rich than that, but yeah, that's one of them.
Right.
It's like sound waves, say. Right? There's a point where you can't detect the sound wave anymore over the random background noise of everything else. Right? That's decoherence. Mm-hmm. Interacting with the environment has meant that you can't see and interact with the wave in its pure form anymore.
I see.
And a good example of coherence is a laser, where you just have a whole bunch of photons exactly lined up in the same state. And you've just added them up. So they make this very powerful laser. Well, there was this idea that everything is in a superposition, but for example, we as people are in a very bad superposition. It's very short-lived because you're decohering faster than... You're made up of a bunch of waveforms that are constantly collapsing. There's this constant evolution because of the information that's leaking away, of people seeing you, of the gravity, as we said before, you're sort of influencing all of these things as your body is moving along.
Yeah. So like that baseball metaphor. Okay. So you explained quantum interference and superposition to somebody, and then they say, oh, okay, so why don't we use that in baseball? So the baseball pitcher throws a pitch and the baseball interferes with itself, and then the batter can never hit it because it's the resolution to that is that, okay, the baseball is interacting with the environment as well. And so the environment kind of collapses the wave function. It extracts the information about where the baseball is at such a quick rate that the baseball ends up only being in one position consistently over time instead of being a superposition of different waves. The environment is just too interacty for it to act like in this coherent way with quantum coherence in order to fool the batter.
The other side of that is the superpositions that exist, which do exist at that scale, even in macroscopic objects. They just are very, very short-lived, right? So it's not. So I think the largest that they're able to demonstrate superpositions of was earrings, diamonds the size of earrings, and you can get those to be in superposition of different states, but that dies in like picoseconds or something, right? So it can be done at pretty.
You mean because of the way that they refract and like reflect light?
Well, light is a super common way of measuring stuff because electromagnetic, and a lot of stuff has some electromagnetic properties. And so if photons are bouncing off of it, usually you could get some kind of interaction, but not always. I mean, if you work in, an ultra high vacuum, really, really cold, like those are kind of extreme environments where you don't get too many photons. Just how measurement can be anything, right? Anything that's where the information's coming out, that counts as a measurement.
So to basically review everything we've talked about so far, in terms of quantum mechanics, things can be in multiple states at the same time, and we call that coherence. And usually in a quantum mechanical system, when you're doing an experiment, you want the system to be coherent long enough for you to do a measurement, which then extracts the information, and you get your really cool quantum result. You get those interference fringes on the back wall. The environment is a third-party player in this, depending on how isolated your system is from the environment, right? So if you sucked all the air and somehow isolated it gravitationally from the outside world, your electrons would interfere for a long time. You could make the box really, really long and still see the interference fringes. But if you let air into the box, if you let the environment have the opportunity to steal that information, the environment will extract that information by interacting with the system the same way you would interact with it by measuring it, and collapse its wave function so that it doesn't stay in that pure, coherent superposition state for long enough to get a really cool.
Right. Every interaction eliminates a whole set of possibilities. Okay.
Exactly. Yeah. But you're not the only person who can interact with the system. The environment can interact with the system as well. Okay. So the clever thing here is that we humans have designed a whole bunch of systems that either take advantage of this or try to isolate it from it. So, I mean, have you ever heard of a quantum computer before?
Mm-hmm.
Basically, the idea behind a quantum computer is that instead of a bit, you get something called a quantum bit, a qubit, which can be in a superposition of the different states. So regular bits in your computers are either zeros or ones. Your qubit can be in a superposition of those two values. And so you can use quantum mechanics to do computations.
Right. And it has to be, it's a little more specialized in the sense that it has to be only one of two states. Like you want a system that can, only take on two states at a given time and not more than that, ideally.
And so the name of the game is, if you're doing one of these qubits, you want your qubit to be super, super isolated from the outside world because, I mean, if you set up your qubit into a nice superposition and say, okay, I'm going to come back later and interact with this qubit because it has some kind of information in it. If you don't isolate it from the outside world will come in and collapse that wave function, and it won't be in a superposition anymore. And then you can't do your computation.
Can I interject a question here? So, okay, if the environment itself is static and measurable, does it just really depend on what your measurement goals are? Because can't you just adjust for that environment, to get a whole series of? Yeah,
definitely. I mean, so for a given qubit, so a qubit being where you've taken some system and you've isolated it. So there's this conundrum that you want qubits to interact strongly with each other, but then you don't want them to interact with the environment, except when you want to sort of control and measure them. So you need like a perfect switch. And like you said, for some of them, it's really just the magnetic field, for example, that if you can shield it well enough, like the Earth's magnetic field and other magnetic fields, then it will be isolated enough that you can create your quantum computer out of these qubits.
Yeah, okay. So the other side to it is, you can take a system and then isolate it, or you can start from systems that are naturally rather insensitive to the environment. And so one example are photons, which are notoriously insensitive. You can, for example, put two flashlights at right angles to one another, and those photons go right past each other, no problem, right? If you do that for baseballs, you don't get the same result. And photons have actually... They have maintained their polarization, which is, one of these quantum degrees of freedom that you can be in superposition. Since shortly after the Big Bang, like you can look at the cosmic microwave background and it's polarized, which is kind of remarkable that you can hold on to superpositions for a super, super long time, so long as you're insensitive to the environment or highly isolated from it, which is the case in space for many things.
Yeah. And I guess to just add to that, I mean, any sort of interesting real world application where we're trying to harness these quantum effects for medical imaging or quantum computing relies on our ability to maintain the coherence as long as possible and fight against decoherence.
So, okay, because I'm used to dealing with visual sound waves in audio editing and whatnot. When two waves are out of phase, they are spatially off from each other in the visual realm. So, if they're at 180 degrees from each other, if Schrodinger's cat was 180 degrees from each other, there would be no cat. It would be completely canceled out. But as they shift in space by degrees from the peaks and troughs of each wave, you get varying degrees of coherence. Does that map similarly in the kind of coherence that you're talking about, decoherence?
Kind of, but it maybe not in the way that you think. So what you're describing, like perfect destructive interference, is still a very coherent thing. The decoherent picture would be everything becomes fuzz.
Ah, interesting. Okay.
So
it doesn't cancel. You're not talking about cancellation. You're talking about fuzz, huh?
Well, it just goes to having no information, right? Like that's another way in which you can imagine like decoherence and manifesting. It's just the loss of information. And so it just becomes bland and gray and 50-50 and, all the textures removed from it.
Right. Interesting.
Because all the information's been stripped out.
Okay, Steph, do you want to talk a little bit about your world record-setting qubits?
I can't compete with 14 billion years from the Big Bang, but the thing from the microwave background is that it wasn't somebody who set a quantum state, like a quantum bit, and then read it out that much later, right? It's not really designing. Like there's less engineering than you'd think. There's a lot more on the discovery side because you kind of have to start with the best ingredients that nature gives you. So something like photons, like that's nature gives that to you, right? So photons are great, but they're not actually the longest lived qubits because they get lost super easily, right? They scatter off things, they get absorbed. And so if you include that, then as your source of noise and loss, then those things aren't as long lived as other objects and other degrees of freedom. We talked about spin a little bit. That's actually a great quantum bit. You can have, in a magnetic field, you can have like a little bar magnet be aligned or anti-aligned with the field, right? And that's the actual analogy for what the spin is for an electron or a nuclear atom. And they can be in both configurations. These are incompatible configurations, just in the same way that the left and the right slits are like incompatible. But you can hold on to both of them at the same time, so long as it's not being measured, right? So long as it's in superposition. So the spin is actually a great qubit for a lot of different systems. And so our strategy was to, start with something insensitive and then isolate it. But it's not maybe the environment that you'd expect. We actually see these like crazy long coherence times, 3 hours. I think we still hold the room temperature record of 40 minutes, which is great. I was pretty happy with that. But it's not in a system you'd expect. It's actually in silicon. So silicon's the material that, our entire supercomputing empire is built off of, right? It's the reason you have all the processing. It's the reason we can have this podcast. It's the reason, all of this. And silicon actually has been made so clean that you get rid of all the noise. So by taking super, super clean silicon, you can have a really, really low noise environment. And by noise, it's the same thing. Like there's no measurements happening. Nothing is talking to these spins because they're very isolated. That was a lot of fun. A while ago now, but yeah, that's the basis of the technology that we're working on. So
Are we talking about official wine cellar room temperature, or is there is there an actual room temperature that you use as a standard, just as an aside?
Yeah, 21 degrees. Like, I mean, at that point, it doesn't really, like, it would be the same, the 40 minutes, it would be the same if it was 0 degrees or 50 degrees. Like, it was very temperature insensitive. Like, that's another one, right? Like, if the temperature changes things, then you're sensitive to temperature fluctuations. And so that can affect coherence. And so you have to find a system that basically doesn't care. It's insensitive to that, because otherwise information leaks out, right? So all that kind of stuff. But if you start from if you start from good ingredients and then you work to, buff up the imperfect parts of it, then you can get these really phenomenal results. So, yeah.
Right. And we're in a very interesting era with, there's this high level of motivation to create a quantum computer, a complete description of a typical quantum state of 300 qubits altogether. So as you can imagine, 300 qubits altogether would be describing, huge numbers of states. In fact, it'd require more bits, regular computer bits, than the number of atoms in the visible universe to describe it. So that kind of computer can do computations that we think just haven't been possible with our regular classical computers. And so, but we're also in this era where nobody's sort of necessarily figured out the right exact way to go about making a qubit. So in contrast to the way that Steph's group has harnessed a particular type of qubit, D-Wave and Google too actually are using loops of superconducting wire where the qubit is made up of current that flows in either a clockwise direction, or so the 0 would be, say, clockwise, and the 1 would be counterclockwise, would be the two different states. And then similarly, in order to isolate that system, it's susceptible to magnetic fields. So you really need to shield magnetic fields. It's susceptible to thermal fluctuations, so you have to make the environment very cold. And then in the materials themselves, the metals that you make the wire out of, or the dielectric that's in between the wires, can have charges or effects that affect the coherence of your system. So it's a different way of going about making them.
Okay, so layman's question here then. In that sort of system with a wire running, you're talking about clockwise and counterclockwise. What are you actually sending through the wire?
In superconductors, what will happen is once you set a current going, it will go forever. And so if that current is running clockwise, that is one of your states. And then if it's sort of counterclockwise going around the loop, then it's your other state. And it can be in a superposition of those two states as long as you don't measure it.
Okay, that's what I was going to ask, because then at what point, doesn't it have to be measured at some point?
Right. So you kind of set your problem, and then you look away, right? You look away from the ghost, and the ghost kind of does its thing, its quantum thing, and it figures out, it does its calculation, and then you check again at the end, and then each qubit has to be having its current going in one direction or the other, because you're forcing it by measuring it. Yeah. And then just kind of coming back to the coherence length, I mean, with the superconducting qubit, the coherence, I think, that's been reached is only about 100 microseconds, just sort of to compare with Steph's, what was it, 40 minutes?
40 minutes room temperature, 3 hours low temperature.
Right. Yeah.
Wow.
Yeah. So
much shorter.
But it's still freaking hard. Like if you cycle, coming back to what Danica was saying, 300 qubits, you think, okay, well, whatever, 300 bits. Like, how many bits do we have in our computers these days? We're talking terabytes, right? Yeah. 300 bits. If that's more complicated than there are atoms in the universe, it's really requires a little bit of engineering and careful planning to control and get good value out of those things. So it's fun.
So, Steph, at the end of the 40 minutes or 3 hours, you're in a state of decoherence. You're not at like a measurable point.
Oh, so you can always measure a system even if it's fully decohered, right? Like,
okay.
It's just what you get at the end is noise, right? Like, it's the same thing. Like, if it goes to static, it's just the information's getting fainter and fainter. And so when people quote a time, it's not as if it goes like good, bad. Like it's a decay, it's an exponential decay. And so they're giving you the time constant, right? So at that point, it's like a third roughly the intensity, as it were, compared to the starting point.
Okay.
And then there's this game of setting your problem and then running it and measuring it. Needs to just be faster than the decoherence time.
All right. I think I'm finally slightly adrift in this conversation. I'm just wondering, like, what is actually observed then at the end of these experiments?
Ones and zeros.
Okay.
Right. So it's digital out, right? So it's just like the right and left slit. Like if you're measuring, which one did it go through, right? It has to tell you one or the other. And so for these systems, it's the current has to be going clockwise or counterclockwise. And for the spin, the magnet has to be aligned north-south or south-north, right? Like that, it can only report one of the consistent values at the end, right? If that's the measurement that you're doing, right? So you set up your measurement to measure that aspect, and then it has to snap to one of those two values.
Right. Okay.
There's sort of another trick, which is that you might, your problem might be like, I want to calculate my taxes. This is a really dumb way of using a quantum computer, but, and you have to then somehow translate that problem to a question that says, take these 50 qubits and tell me what state they're in at the end.
Okay. I think I get it.
So like in a regular computer, how it works is your computer starts out with a whole bunch of ones and zeros in it. You enter your taxes and your computer goes, okay, this is a whole bunch of ones and zeros. And then the computation involves making those bits interact. So there are some parts of the computation where it's like, okay, so if this is a 1 and this is a 0, I'm going to write a 0. And then there's another part that's like, okay, so if these three are 1s, then I'm going to write a 1. And then that's essentially the calculation your computer's doing. It's just comparing bits. In this case, what happens is you're making the bits kind of interfere with each other, and they're kind of they're all superpositions. And so the way they interfere with each other will kind of depend on the superpositions they're in. But then, so essentially, you're doing something analogous. You're making the computer compare these bits, but instead of just going, okay, if this is a 1, this is a 0, you're like, okay, I'm going to take this one, and then somehow I'm going to make it interfere with the signal from this one. And then you make it run its course. And because they're all superpositions of each other, the final result, when you do the measurement, will say, okay, I've done the measurement and it's a 1. Or I've done the measurement and it's a 0.
Okay.
And it will give you the correct answer, even though throughout the calculation, each of the bits wasn't a 0 or a 1.
So every if is still binary, but it's the then that changes.
Not really. So it's so much more than that, and also so much simpler. Like, so the model is just, the way that you process stuff is different. So for the people in the audience that have done any coding, and maybe this is not the right analogy, but basically the fundamental units are not if and then statements. The fundamental units of operation are matrix multiplication and matrix operations. And so you can try and massage all your matrix multiplications into if and then statements, but that's very different than the native operations of these things, right? Is that helpful at all? Like it's the language. Yeah. The language is fundamentally different.
I think it is. I'm still having trouble understanding how this doesn't still boil down to like a massive series of if-thens.
Oh, because so the size of the matrices is where it kind of gets crazy. So the 300 number that Danica came up with, the matrix is then a 2 to the 300 by 2 to the 300 matrix, and the number 2 to the 300 is bigger than there are atoms in the universe. Like it's a really big number. So that matrix, I mean, that's what we would do to represent the system, but that's actually happening on, if you have 300 atoms in a molecule in like a protein in your body, that's happening all the time. Right? That operation is happening all the time. And so that's so much more than if then. And so you can't really boil it down once you're at those scales. It's just that mapping isn't, it doesn't show you the real power. Now, I should say that classical computing, like the ones and zeros, that's a subset of quantum, right? So if your quantum bits were sufficiently crap, they're just classical. And so then you could
really easily imagine how you'd map that to just if-then statements in the kind of traditional way that we think about processing information. But what's actually happening are these big matrices are kind of acting, at least mathematically, that's what's happening, right? How you would describe it. And so if you start using that as your fundamental unit, it opens up a lot more capability.
Yeah. Okay. I think I get that.
Yeah?
I think so.
Cool.
Yeah.
Yeah. It's just a different picture. And that's why it's going to be so hard to shift, because it's not like we're talking about CPUs to GPUs when we're talking about these technologies.
Yeah.
It's just like, it's a very different thing, because you can't just say, okay, well, here's how you do an if then, or this is what the while loop looks like. I mean, it's nothing like that. It's just a completely different way of programming. And so the retraining to use these things is going to be kind of a big deal. But the power that you get from it is worth it.
So you might be familiar with the hype for quantum computing. The story is that there are some calculations which are computationally hard, like the traveling salesman problem, for instance. They're just like, the more options you have, the more possibilities, dramatically increases the number of outcomes. And so a computer is going to take longer and longer and longer to sort through all the possibilities, because a classical computer would have to calculate each one individually, and that takes exponentially longer. So the idea is that the quantum computer in its framework is so different from the classical computers that you can use quantum computers to do calculations like the traveling salesman problem and solve them.
You're on a roll.
You can't do traveling salesman? Okay.
No, so that's one that's bandied about a lot. It's the complexity arguments on that are less clear than some of the other applications, but traveling salesman is meant to be it's a so-called NP complete problem. And that we don't hope that quantum computers have a go at that. Nobody really expects to hit those kinds of problems, but that doesn't mean that there aren't exponentially challenging ones like protein simulations, right? Like the simulation of caffeine, that is well within the wheelhouse of quantum computers. For example, caffeine is beyond the scope of current conventional computers to simulate, because the atoms involved all can interact with all the other atoms and all the other chemicals in superposition, right? And so that inherently involves a lot more complexity than our classical approximations are able to handle. Our classical computers just can't give it a go. And so the prospect of simulating chemicals is just way outside this. Like we just do a really bad approximate job, and we'll always do a bad approximate job because of the limitations of the way that information is processed classically. But if you use quantum to simulate quantum, you have a shot, right? And so that's one of the, I think, the easier ones to point to. Traveling salesman, there might be some approximate things, like some optimization stuff that it could speed up. So you're not entirely wrong.
Right. Well, the three main application areas I think people think are worth exploring right now is this sort of quantum chemistry, as Steph alluded to, as well as heuristic optimization, which is sort of this idea that it's an optimization problem with not one clear solution. And I like to think of an airport with a bunch of planes, a bunch of gates, a bunch of passengers, and a bunch of luggage and staff. And you have to sort of come up with something that's overall optimizes coordinating who goes where and what goes where.
Yeah, so you can do a better job, but the calculation of the optimal is maybe outside the scope, but that doesn't mean that quantum couldn't be substantially better, right? I guess that's the picture.
Is there chance involved in those calculations? Is there, I guess when you're saying like using quantum to simulate quantum, I mean, is there, is the chance of arriving at the solution that you want predictable, or is that unpredictable?
Oh yeah, it's probabilistic.
So there's two kinds of quantum computation strategies. One's some of them have probabilistic answers. So like a lot of the heuristic ones are probably in that category, but there are deterministic ones, right? So there's like the famous Shor's factoring algorithm. That one produces a result, And so you run the algorithm and you get a definitive answer at the end. And that is totally possible because you just have in the interference picture, you have perfect interference, constructive interference on the right answer and destructive interference everywhere else. Right. But there are algorithms. And so when you measure it, it tells you the right answer. But there are other algorithms that produce a probability distribution that is just heavily weighted towards the right answer. Right. So you get, you'd run it and then, maybe you run 100 times and 40 times it would give you some number and that's the likely answer or whatever. That's a high probability result. And then you get a bunch of other results, which are less useful. And so those kinds of algorithms are super good when you can actually check how valuable the answer is at the end. So for example, you could run a ground state calculation or something like that. And so one answer will have a certain energy and then the other answers will have different energies. And you can just say, oh, well, this one is the lowest one that came back. And so that one's the right answer, right? If it has some way of measuring the quality of the output at the end, then those ones are really, you can use them pretty well.
Okay. No, that makes sense though.
The answer is both, both probabilistic and deterministic.
Yeah.
It's just, there's so many different algorithms out there, right? They're all kind of different.
Yeah, so quantum computing can take advantage of a phenomenon known as tunneling or if you can cast your problem as sort of a landscape, an energy landscape where each final solution represents like a higher or lower energy, and you're looking for an optimal configuration, which would be represented by a lowest energy state, then where a classical computer would have to kind of search the space, like think of like an actual like landscape where you would have to go and set out and walk up over the mountain or around the mountain. And quantum computing qubits allow you to like just tunnel straight through the mountain down into the valley on the other side.
Right. Okay. Yeah.
Okay. So there's one last topic I want to mention. In quantum computers, you want to isolate your qubits as much as possible from the environment. Decoherence is bad. As we said, though, decoherence depends on how the environment specifically is interacting with your system, right? So there are some systems that depend on decoherence as part of the mechanism to be useful.
This is the example I like to use to kind of bring it home to people and say, hey, look, like we're using quantum stuff already. We're using these properties for technologies right now and just maybe not the language that you're used to hearing. So MRI machines are basically, they're controlling the quantum property of spin within all the water molecules that are being looked at in the MRI machine. So if you're in an MRI machine as a human, you have a whole bunch of water. And so what the MRI machine is doing is kind of probing and measuring the spin in aggregate, what the spin states are for all these different water molecules in your body. And so it relies upon the fact that in some environments, you have a lot more water, and so the water talks to each other, and so that's a form of decoherence. And so you get a very different decay than you would in other parts. And so that can actually be used to infer what the density of the water is. And so that's how you get your image. Like it tells you, okay, that's how much it decayed there, and there's your image. So you're already using...
No idea.
Yeah.
That's fascinating.
Yeah. So those spins, that's why it's kind of helpful, because those spins, they're so isolated from the environment, and that's why their MRIs are so safe, even if it has a loud clicking sound. Is the reason why this works is spins basically just don't care about the environment. That's why they're such good quantum bits. But that means that there's no likelihood that changing or measuring the spins is going to have any real effect on anything else in your body at all. And what you're measuring is how long they're away from their so-called equilibrium state, because they all settle down, right? They all settle down into where they want to be. And then when you're measuring it with an MRI, you kind of knock them out a little bit and then just measure how long it takes for them to get back. And so it's a kind of, it's measuring the quantum properties and that decay.
Literally, the magnets are affecting the spin and measuring that.
Yeah.
I had no idea. That makes so much sense, of course.
Yeah. In an MRI machine, you got a big honking magnet, and it flips all the spins of the water molecules in your body. And then over time, they'll just reorient themselves. But the time scale it takes to reorient themselves depends on how the environment around those water molecules are interacting with them, right?
Right.
Yeah. And it's not just water, but that's the easy one to think about, right? Like,
Yeah.
You're measuring the decoherence time.
Yeah, and that's the same technology
Right.
that we use to actually control our quantum bits. The exact same technology. It's called magnetic resonance. So MRI is magnetic resonance imaging. And you also have
Right.
something called NMR, nuclear magnetic. It's the same thing. It's the same
Wow.
thing.
As big and scary as MRIs are, that's actually a really interestingly humane method of probing the
Oh, yeah. No,
the, body.
it's super
Yeah.
safe. Yeah, because it doesn't interact with anything else. So.
Well, that was fantastic. Thank you, Stephanie. Thank you, Danica. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit. Dr. Stephanie Simmons, you get a mango.
Num, 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 num.
And Dr. Danica Marsden, you get a raspberry. I'd like to thank my guest, Ted Leo. For links to Ted Leo's new podcast, visit our website. Thank you, Ted, for coming on.
Thank you. I don't get a fruit.
Everybody wants fruit these days. You got the fruit of knowledge.
Oh, that's true. That is very true. Original sin.
That's right. Yeah, that's us. We're the snake in the tree,
right.
I guess. All right. Well, that was absolutely fantastic. Okay, everybody, it's time for the announcements and the great reading of the names. So the hiatus is over, as I've mentioned, for a few months in a row, and we are now on the phase I call March to 100. So monthly episodes, we've been going strong, and we're going to keep going strong. Now, so second announcement. We're having a live show in February. This is our first live show ever. We're doing it at the AAAS 2020 General Meeting. I guess they regularly have a day or two of live podcasts, so we're going to be participating this coming February. We're recording on Sunday. You can buy a one-day pass to come and hear us talk and wander around the conference today if you would like, but I will also be releasing the audio as that month's podcast. Third announcement. Let's mention all of the different places you can listen to the Titanium Physicists. Now, seeing as you're listening to this right now, I am confident that you know how to do it in one way or another. But if you're going to tell your mom and uncle and internet best friends about us, you might want to know that we are available on their favorite way to listen as well. We are available on Stitcher, Google Play Music, Spotify, Pandora, YouTube, and of course, iTunes. Fourth note, I'm doing a thing where if I cannot find a cool guest or our planned guest cancels at the last minute, I'll choose a listener of the show to sit in the guest chair and chat with us about physics. In order to be a guest, you need three things. The first is to follow us on Twitter or Facebook because that's where I make the announcement. Usually I'll say, hey, we need a guest tomorrow afternoon. If you are willing to be a guest, please respond to this message in the next 3 hours, something like that. The second thing you need to do is have a fast internet connection at home and a quiet place in your home or workplace or wherever so that we can get good quality audio from you. The third thing is you need to be available when we want to record. But those are it, those three things. So follow us on social media and you might get lucky. The fifth announcement is that our email address is barn@titaniumphysics.com. I haven't mentioned this in a while, and so I thought I should mention it today. I note, though, I don't write back very often because I'm fairly bashful, and I often don't have time to write long answers to interesting and good physics questions, and so I put them in a pile to maybe use when we restart Question Barn. But you might need to contact me for some reason or another. Maybe I switched the audio tracks and you can't hear us very good. So that's our email address, barn@titaniumphysics.com. Finally, we are still humbly soliciting your donations. Your donations go for paying our server fees and for our episode transcription project and for buying our physicists' microphones. You can send one-time donations through PayPal off of our website, or you can go to our sweet Patreon site and give a recurring $2 or $5 donation. If you give more than $2 and supply your address, I'll send you a postcard. Eventually. This particular episode of Titanium Physicists has been sponsored by a collection of generous people. First, I'd like to thank the generosity of Brian Cook. Thanks. Okay, and now I'd like to thank our Patreon sponsors. Thanks, C-Peel, Mark Painter, Tyler Durden, Veronica Cookie Monster Galdino, and Mr. Mike Forrest. It's Skytimer with Raven Bell, Dan Marr, Amir Bani Asadi, Cassandra McCarthy, Christoph Beatty, Mr. M.M., The Wild Drew Hickox, The Master Oscar Delgado, Callan Richardson and Joe Campbell, Asharan Banagiri, J.P. Raudio, Aaron Wheeler, Sander Boros, A Badger, The Septet Baylor Fane, and Luke Edwards, Mr. Astro Yuki, Shivang Patel, Mr. Martin Mihulka, Henry Rabung, Peter Scott, Russ Mutsi, Ayush Singh, and Matthew Sullivan, Daniel Lauzon, Patrick Eon, Kevin Forsyth, Yer Panay, Hoinam Duong, Stian Henriksen, a TPR Jones, Pascal, a Mr. Ryan R., a Mr. Michael Usher, Senior Canada, Adrian Schoenig, Sarah Stradler, Louise Patinella, a guy named Ben, a Mr. Matthew Lambert, a fellow named Ayush Singh, a David Myrtle, Mr. Ryan Foster, a Janico Freffenberg, Steve Smethurst, Magnus Christensen, Bart Gladys, a Mr. Stuart Pollock, our Pirate Emperor Calico Davis, Mr. David Lindels, Mr. Carl Lockhart, our eternal friend B.S. and Randy Dalzel, Miss Tina Raudio, the enigmatic Ryan, a gentleman named Crux, and Gabe and Evan Weens, David D., Dan Vale, a Mr. Alex, WTL, a Mr. Per Proden, Andrew Waddington, Mr. Jordan Young, John Bleasy, a Brittany Crooks, James Crawford, Mr. Mark Simon, Tucson's gang of one, Mr. Lawrence Lee, Sixton Linnison, Mr. Simon, Keegan Eade, Andreas from Knoxville, Cadby, Joe Campbell, Alexander Zani is great, Winna Brett, Eric Dutch, Etienne, a gentleman named Peter Fan, Gareth Eason, Joe Piston, David Johnson, Mr. Anthony Leon, as well as Doug B., Julia, Noah Robertson, Ian and Stu, Mr. Frank, Philip from Austria, and Noisy Mime, Mr. Shlomo Dalal, Melissa Burke, Yassine Urzazi, Spider Rogue, Insanity Orbits, Robin Johnson, Madame Sandra Johnson, Mr. Jacob Wick, Mr. John Keys, and Mr. Victor C., Ryan Kloss, Peter Clipsham, Mr. Robert Halpin, Elizabetha Teresa, Rob, and Paul Carr, Mr. Ryan Newell, Mr. Adam K., Thomas Shire, Mr. Jacob S., a gentleman named Brett Evans, a lady named Jill, a gentleman named Greg, thanks Steve, Mr. James Clausen, Mr. Devon North, a gentleman named Scott, Ed Lowlington, Kelly Wienersmith, Jocelyn Reed, Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. So that's it for Ti-Fi this time. Remember that if you like listening to scientists talk about science in their own words, there are lots of other lovely shows on the Brachial Media Network. The intro song is Tell Balgary Balgary's Dead by Ted Leo and the Pharmacists, and the end song is Russia by Ramona Falls. Good day, my friends, and until next time, remember to keep science in your hearts.
I visited Russia and I started folding until in one precious doll I had poured in all of Siberia, and I said, love, here ya go. She said, too little too late. Took to the Nile, where I started swimming upstream till I found we found the spring burning with God's purest water from above the Father to heal her.